Welcome back. We're in chapter 14 on acids and bases, and we're now in section 14.5, which is the ionization of water. I know I've told you, whether you've heard or not, it's a different story, that if you were to put just a glass of pure water on the table, some of that water is going to break apart or dissociate into protons and hydroxide. Water is HOH. And if it breaks apart, it's going to break apart on one of the bonds of the hydrogen and oxygen. And the oxygen is going to steal the electron and become at OH, negative 1. The other one will be the proton, H positive 1. When an H positive 1 is sitting in water, it will react with water to form an ion called hydronium, H3O positive 1. So what you're going to do is, if you were to take a glass of water, and that would be your whole experiment, is just put some water in a glass. That's an easy experiment. It's a hard lab report, but an easy experiment. You're going to find that some of that water is going to dissociate. You could then measure the concentration of hydroxide ions in the water, and you could measure the concentration of hydronium ions in the water. Okay? This is called autoionization. It by itself ionizes. The water is acting as the acid, and the water is acting as the base. An acid, remember, is a proton donor. So if it breaks apart and donates a proton, it's acting as the acid. A different water molecule is also acting as the base to receive that proton and become an ion. Since you can then measure it, you could get a K, you could get a constant to tell you how much are you going to get. Are you going to get lots and lots of product, which in this case is the hydroxide and the hydronium, or are you going to have mostly water in that water? I'll give you a hint, it's probably lots of water in that water. So you're going to have a very, very small amount of hydroxide and a very small amount of hydronium. If you measure it, okay, so here's what's happening. You've got a water molecule breaking apart, and then when it breaks apart, this proton is joining with the other to make an acid. So here's the base, it's receiving the proton. Here's what's left over, this becomes the hydroxide. Here, this is the water that's receiving it, it's acting as a base, so this one jumps over to here, becomes H3O+, that's now the acid. Okay, so this is water acting on water. Water is an acid, and different water molecules a base, creating its conjugate acid, hydronium, and its conjugate base, hydroxide. Okay, so what you're going to see is, if you actually were going to measure that, you could measure it, and it's completely consistent all the time. You are going to get a measurement of hydronium at 1.0 times 10 to the negative 7 molar, and hydroxide also at 1 times 10 to the negative 7 molar. Okay, you're going to get just as much hydroxide as hydronium, and it's going to be a very small amount, 10 to the negative 7, very, very small. That tells you that your ionization constant for water is negative. It's got a negative 1 times 10 to the negative something. So mostly you're going to end up with water in that glass of water, but a little tiny bit of ions. Okay, so you're going to have a very small ionization constant. If I were to not just have water, but I also add some acid, okay, so I'm adding acid to my water now. Let's imagine of what's happening just in the water. Some of the water is breaking apart into acid and a little bit of base, and if I add more acid, it's going to have lots and lots of hydrogens to donate and lots of water to accept it. The water is going to accept those hydrogens, and so you're going to end up with a hydronium ion concentration that's higher than it would if it were just a glass of water. Okay, by adding acid to that water, you're going to get more hydronium. That's acid. And that acid is going to show up with a higher hydronium. So you're going to have a higher hydronium and a smaller hydroxide. Okay, so you're going to have a much you're going to have a different number. It's going to not be 10 to the negative 7. It's going to be a higher molarity than 10 to the negative 7. Your hydroxide is going to be a lower molarity than 10 to the negative 7. Okay? Conversely, if I add a base to water, a base, remember that's like something hydroxide. Well, if hydroxide is my conjugate base for water, OH, and I add something that's going to give you lots and lots more OHs, then you're going to see that your OH concentration is going to go high, and your acid concentration is going to go down. So your hydroxide is going to exceed 10 to the negative 7. Remember, 10 to the negative 7 is just a glass of water sitting by itself. If I add some base, I'm going to have more hydroxide, obviously, and less acid. Okay? Let's compare them. In an acid, if you add acid to water and you have an acidic solution, you're going to have more hydronium ions, and you're going to have less hydroxide ions. Okay? pH is the concentration of hydronium. If you have something that's acidic, you're going to have a higher concentration of hydronium. If you have water, you're going to have equal concentrations. If you have a base, you're going to have a lower concentration of acid and a higher concentration of hydroxide. So, an ion product constant, okay, so remember all these constants are simply telling you, are you going to have more product or are you going to have more reactant? Are you going to have something on the right? You'd have a big number, you'll have more stuff on the right. If you have a little number or a negative exponent, you're going to have something on the left. Well, on the left, okay, remember, is pure water. So if I have on the right hydronium and hydroxide, and on the bottom I had pure water, which I'm going to ignore, then my K sub W, or my ion product constant for water, how much ions is it producing, this is, remember, just a glass of water on the table, would be the concentration of hydronium, which we saw measured was 10 to the negative 7, and hydroxide, which is also 10 to the negative 7. That means that pure water will have a concentration of 10 to the negative 14. It's almost all water. It's only a tiny, tiny little bit of ions. Okay? But this number, 10 to the negative 14, is going to be very significant because we're going to see that the pH scale only goes to 14. It's going to be a number between 1 and 14. Anything towards 1 is going to be highly acidic. Anything towards 14 is going to be highly basic. All right? We'll get more to that later. So let's look at neutral. Neutral would be like a glass of water. Water is just as much hydroxide as it is acid. So it's half and half. It's equal. So we're going to call that neutral. It's neither acid nor base. Water, we're going to see later, has a pH of 7. That 7 is coming from this negative number. That's where we're going to get the 7. Okay, so if it's neutral, it's going to have a acidic or an acid, this is hydronium, which is your acid, concentration of 7. That's the pH of 7. Anything that's very, very, very basic, okay, is going to have a pH towards 14. And because the Kw of water is the acid times the base, 7 and 7, remember, you're adding the exponents when you multiply these two numbers, and you get 10 to the negative 14. So 10 to the negative 14 is the amount that water breaks apart. Anything that's acidic, some of that OH is going to go down and the acid's going to go up. Anything that's basic, your OH goes up and your hydronium goes down. So if you were to have a problem, really all you're going to do is fill in what you know and solve for what you don't know, just like any algebra problem would be. So let's look at this. K sub W is going to be, if you remember, it's going to be pure water on the left, hydronium and hydroxide on the right. So if you're going to do a constant, you just do the concentrations of anything that's aqueous and ignore the stuff that's pure. So the water was pure water, it was a liquid, so we're going to ignore it. So your concentration is going to be the K sub W, or your ion concentration constant, is going to be your concentration of acid, hydronium ions, times base, divided by 1. And we're going to see that K sub W is always going to be 1 times 10 to the negative 14. So that's something that you can actually always know. I mean, I'll give it to you always. It doesn't change. The amount of ions that break apart in simply setting a glass of water on the table, the amount of ions is going to be 1 times 10 to the negative 14. That's a very, very small amount. Mostly it's just water there. Now, if I know that number, 1 times 10 to the negative 14, that's what we're going to call K sub W, always. It never changes. So if I'm given some other things, I can solve for whatever I want. So here's an example. If hydroxide is this amount, 5 times 10 to the negative 8, how much acid's there? Well, I have 2 things, and I'm solving for 1, so it's not hard. The K sub W is 1 times 10 to the negative 14. Your acid they give you is 5.0 times 10 to the 8. That goes here. And then you solve for the OH. So when you solve for the OH, or you solve for the hydroxide, I'm sorry, you're going to get 2 times 10 to the negative 7. And that is how you're going to figure out how much acid is in something if you know the concentration of the other one, because you've got everything you need. This is something we should do in class, and we'll do some examples, and I think it's not as hard or scary as it looks. I'll see you in class.